Hello everyone, welcome back to this online class. Today we are going to look at the numerical differentiation technique, and we have this example. We are asked to discuss numerical differentiation and hence work out the following question. So we are given the table of data x versus f of x. There are 3 data points. We are asked to find f prime of 1.1 and f double prime of 1.1 using part A, Lagrange technique, part B, Newton's divided difference technique, part C, Newton's forward difference technique, and part D, Newton's backward difference technique. So first of all, let's talk about numerical differentiation. You see, just the usual differentiation that we learned in calculus. Those are the same technique we are going to apply here. But now when we talk of numerical differentiation, this is what it means. So you can write numerical differentiation. So it is based on the interpolating polynomials. Is based on the interpolating polynomials. And you see, we have learned 4 interpolating polynomials. There's Lagrange, there's Newton divided difference, there's Newton forward difference, and Newton's backward difference. Those are the ones we've learned so far. And so once you've found the polynomials, you need to differentiate them as usual. If you have to apply chain rule, if you have to apply product rule, if you have to apply power rule of differentiation, etc. Same techniques of differentiation, as long as you have the interpolating polynomial. So the polynomials are denoted by Pn of x. And we've seen how to get this polynomial using Lagrange technique. We've seen how to get it using Newton's techniques. This is Lagrange technique. When I talk of Newton's techniques, there are 3 of them. The first one is forward. Another one is backward. And another one is divided. Those are the Newton's technique of obtaining the interpolating polynomial Pn of x. So once you have the polynomial, what are you supposed to do? So now, to get f prime of x is approximately equal to Pn prime of x. And when we write f prime, it means derivative with respect to x. So this is equals to derivative with respect to x of Pn of x. When you want f double prime of x is approximately equal to Pn double prime of x. So this is the second derivative. So this is d squared over dx squared of Pn of x. etc. Higher order derivatives are evaluated in the same manner. So having talked about how to get the derivatives, let's now answer the question so that you'll be able to understand those techniques better. And you see, when you have a function of s, like in the case of Newton's forward and backward difference techniques, you are going to use chain rule of differentiation. So in fact, we can take note of that. You can write a note. In the cases, or for the cases, for the Newton's forward and backward techniques use chain rule of differentiation. Because why are we using chain rule? Because you see our polynomial in Newton's forward and backward was a function of s, not x. So if you want to differentiate it with respect to x, you'll have first of all to differentiate with respect to s and then times ds dx. And remember, in those cases, we said s is equals to x minus x naught over h. So this means if you want to get ds over dx, this will simply be 1 over h. We are going to see how to get that. So let me give you an example. Of course, the example is here. We have the table. I want us to obtain the interpolating polynomials for each case and then see how to differentiate that polynomial. So we start with part A, the Lagrange technique. Of course, as you know, this will be our x naught, x1, x2. When it comes to Lagrange technique, this is f naught, f1, f2. So now, let's start with part A. We work out the question. So you can write here, work out the question. In part A is the Lagrange technique. What do we need? We need a polynomial to be able to fit that data. Our data has 3 points. So the data has 3 data points. 3 data points means our polynomial should be of degree 2 to P2 of x. It must be of degree 2. So by the Lagrange technique, P2 of x is equals to the sum from I is equals to 0 to 2 Li of x, f of xi of simply fi. And so when you open it, you're going to get, when you open the summation, that's what I mean, you're going to get L naught of x, f naught, plus L1 of x, f1, plus L2 of x, f2. Let's get the Lagrange coefficients. So you can say now our L naught of x is the same as x minus x1, x minus x2 over x naught minus x1, x naught minus x2. And so this, when you work it out, we'll get x minus x1. Look at your table. In that table, our x1 is equals to 1.2, and the other one is 1.4. Then this is over 1 minus 1.2, 1 minus 1.4. When you press that in your calculator, you need to get, of course you can work it out. Let's see what you're going to get. So when you expand that, you need to get 25 over 2 25 over 2 times x squared minus 2.6x plus 1.68. Let's work out the other one. L1 of x. That's the same as x minus x naught, x minus x1. No, that should be x2. Because denominator there should be x1. So that should be x minus x2. There's no x1 in the numerator. Take note. So denominator will have x1 minus x naught, x1 minus x2. So again, if you substitute, you're going to get x minus 1, because x naught is 1, x minus 1.4 over 1.2 minus 1, 1.2 minus 1.4. That should give us negative 25 times x squared minus 2.4x plus 1.4. Finally, L2 of x, L2 of x, that's the same as x minus x naught, x minus x1, everything over x2 minus x naught, x2 minus x1. Again, if you substitute the constants, you're going to get x minus 1, x minus 1.2 over 1.4 minus 1, 1.4 minus 1.2. If you simplify again, you need to get 25 over 2 times x squared minus 2.2x plus 1.2. Now let's substitute this back to our polynomial so that we get it as a function of x. So you can say that therefore our P2 of x is equals to L naught times F naught. So that's 25 over 2 x squared minus 2.6x plus 1.68. What was the value of F naught? You can read it from the table. That was 0.1. Then plus, that will be minus now, minus 25 x squared minus 2.4x plus 1.4. F1, that was 0.5. Then lastly, plus 25 over 2 x squared minus 2.2x plus 1.2. F2 was 0.8. So let us simplify this expression so that you see what you get. We need to simplify even before we proceed to find the derivatives. So when you simplify, this is what you need to get. Negative 5 over 4x squared plus 19 over 4x minus 17 over 5. Now let's now find f prime of x and f double prime of x. So you can just say now hence, right, hence f prime of x is approximately equal to P2 prime of x. When you differentiate, you get negative 5 over 2x plus 19 over 4. F double prime of x is approximately equal to P2 double prime of x. So it's just the derivative of the first derivative, that is negative 5 over 2. So now at 1.1, f prime when x is 1.1, that should give us negative 5 over 2 times 1.1 plus 19 over 4, and that is 2 f double prime. When x is 1.1, that should give us simply negative 5 over 2. It is a constant, which is negative 2.5. So that's how to use the Lagrange technique of interpolation to obtain the derivatives of the function. Once you have the polynomial, you simply differentiate it to get f prime and f double prime of x and evaluate at the indicated value of x. Part B, we answer the same question, but now in this case, we are using Newton's divided difference technique. So you write part B. Part B, we are using Newton's divided difference technique. So you come up with the divided difference table. I'll need x values here and f of x values here. There's a horizontal line and a vertical line. So we can list the x values, that is 1.0, 1.2, and 1.4. Also list the corresponding f of x values. Here we have 0.1, 0.5, 0.8. So the first order divided difference of f, just subtract 0.5 minus 0.1, that is 0.4. Let me just write 0.5 minus 0.1 divided by 1.2 minus 1.0. So that's 0.4 divided by 0.2. You can press that in the calculator. 0.4 divided by 0.2. That should give you 2. Do the same. 0.8 minus 0.5 divided by 1.4 minus 1.2. Again, that is 0.3. We are dividing that by 0.2. And so that is 1.5. Let's get the second order. D squared operating on f. That will be 2 minus 1.5 over 1.4 minus 1.0. So 2 minus 1.5, that is 0.5. Then divided by 1.4 minus 1.0, that is 0.4. So divided by 0.4, that is 1.25. 1.25. So that means our polynomial must also be of degree 2, because look at the last column, that is d squared, a second order divided difference. So now this is our x naught. That is x naught. So this one here is x1. And this is x2. Again, those values of f of x here will have f naught. In the formula, we only need f naught, and so this will be our b naught. This other value here is our b1, and this other value is our b2. So the polynomial takes the form p2 of x is approximately equal to, not approximate because this is a polynomial, so that is equals to not approximate, is equals to b naught plus b1 times x minus x naught plus b2 times x minus x naught x minus x1. So you need to substitute those values of the constants b naught, b1, and b2, and also x naught and x1, so that you see what you get. So even before we substitute, there's something here that we need to correct. Instead of 2 minus 1.5, it should be the other way around. It should be 1.5 minus 2. The next minus the previous, so 1.5 minus 2. Only the sign changes. So we expect this to be negative instead of positive. So just change the sign. So that should be negative 1.25. The sign changes because we are subtracting the other way around. So now when you substitute B naught, you get, let me use another color. That should give us 0.1 plus our B1 is 2 times x minus x naught is 1, then minus 1.25 times x minus 1 times x minus 1.2. And so when you simplify, you're going to get negative 1.25 x squared plus 4.75x minus 3.4. So that's what we get. And you see, it is the same as what we got in the Lagrange case. Let's see, what is 17 divided by 5? That is 3.4. What about 19 divided by 4? That is 4.75. And 5 over 4 is 1.25. So the same polynomial that we got in the Lagrange case. So, or in terms of fraction, this can be written as P2 of x is the same as negative 5 over 4 x squared plus 19 over 4, then minus 17 over 5. We have found the same polynomial, just like when we used Lagrange interpolation. So now let's get the f prime and f double prime. Of course, you can see them from here. I don't need to work it out again because already we are differentiated and we found it. So you can say therefore, f prime of 1.1 is approximately equal to 2. And f double prime of 1.1 is approximately equal to negative 2.5. Same values. Now part C, we are now going to use the forward difference technique. So you can write part C. We are now using the Newton's forward difference technique. Again, you need to come up with the difference table. We'll have x versus f of x. So there's this horizontal line and the vertical line. X values is 1.0, 1.2, 1.4. Here we have 0.1, 0.5, 0.8. So the first difference, the first order difference, that is delta F, that will give us, just subtract 0.5 minus 0.1, that is 0.4. Here we have 0.8 minus 0.5, that is 0.3. Go to the second order, delta squared F. Again, if you subtract, you're going to get 0.3 minus 0.4, that's negative 0.1. So that's our table for the forward difference. Now, what is the polynomial? Our polynomial in this case is also of degree 2. P2 of x is equals to f naught plus s times delta f naught plus s minus 1 over 2 factorial delta squared f naught. So look at our value of x that we need to approximate. It is at 1.1, which is somewhere here, 1.1. So we are going to pick our x naught to be a value that is above 1.1 in the table. So of course, as usual, it is 1.0. Let this be x naught. And so now it means this will be our f of x naught, which is f naught. So with forward differences, you read them along this line that is sloping downwards. So the value here is delta f naught, first order forward difference of f naught. And this other value is the second order forward difference of f naught. So how do we get s? This is x, our x is 1.1. So we say let x be 1.1 so that our x naught will be 1.0. So our s is equals to x minus x naught over h. What about h? Look at the spacing between the x values. That is 0.2. It must be uniform. Remember, if the spacing is not uniform, then you cannot use this formula. H is 0.2, the uniform spacing between the x values. So when you substitute, you'll have 1.1 minus 1.0 over 0.2. And so that is 0.1 over 0.2, that is 1 over 2, or simply 0.5. 0.5. So let's now substitute them back into our polynomial. So therefore, our polynomial will now be written as f naught, which is that is 0.1. So I don't need to replace s now because you see I'm going to differentiate. So here there's no need of replacing s. Let's leave it in terms of s first of all. So plus s delta f naught is 0.4, and then plus s minus 1 over 2 factorial, a second order forward difference of f naught, that's negative 0.1. And so let's again simplify this so that we leave it as a function of s. Let's see what we are going to get when we open all those brackets. So when we simplify this, we need to get negative 1 over 20 s squared plus 9 over 20s plus 0.1. Remember, this is a function of s. It is P2 is a function of s. So that's our interpolating polynomial for the case of Newton forward difference technique. Now let's get f prime of x, and then we evaluate when s is equals to 0.5. So now f prime of x is the same as d dx, or simply approximately equal to d dx of our P2 of S. So you have to use chain rule of differentiation. So this will be derivative with respect to S of P2 of S times ds dx. Remember I told you from here, you can be able to differentiate S with respect to X. So from here you can get ds dx to be 1 over h. 1 over h. So this you write as 1 over h times dp2 of s ds, which is also equal to 1 over h is the same as 1, our h is 0.2, so 1 over 0.2. When you differentiate p2 with respect to s, you get negative 1 over 10 s plus 9 over 20. That's the first derivative, our f prime of x. Let's get f double prime. F double prime of x. That is approximately equal to derivative with respect to x of the answer we have found here, of course, of f prime of x. And what was our f prime of x we replace with that answer? It will be d dx. Our f prime of x, we have 1 over 0.2 times negative 1 over 10s plus 9 over 20. You see again, this is a function of s, so I have to use chain rule. So you differentiate it with respect to s, d ds of the whole of this 1 over 0.2 negative 1 over 10 s plus 9 over 20, then times ds dx, which is 1 over h. So that's the same as 1 over 0.2. Remember, this is 1 over h, so 1 over h. And h is 0.2, so 1 over 0.2 times, when you differentiate this bracket, you're going to get 1 over 0.2 times negative 1 over 10. And so that should be able to give us 1 over 0.2 squared times negative 1 over 10. That is simply 0.4 times 10. So negative 1 over 4. Which is the same as negative 2 point, no, we are saying 1 over 4 as a fraction, that's negative 0.25. So that's what we have there. Now, when s is equals to 0.5, what do we get? So you write f prime of 1.1. When you transform it, it will be approximately equal to, because 1.1 will take you to s is equals to 0.5. So that would be 1 over 0.2 then times negative 1 over 10. S is 0.5 plus 9 over 20. So press this in your calculator. Let's see what you're going to get. 1 divided by 22 multiplying negative 1 over 10, which is 0.1, times 0.5 plus 9 over 20. That should give us 2. So that's f prime of 1.1. Also get f double prime of 1.1. So you can write here f double prime of 1.1 is approximately equal to. So do the same thing. Remember now you substitute s is equals to 0.5 in this formula for f double prime. Let me take you back to what we got here. This was not 1 over 4, but 1 over 0.4. Take note, it was not 1 over 4, but it is 1 over 0.4. So when you divide, you get, instead of 0.25, you'll get negative 2.25. So that f double prime at 1.1 is simply the same constant, negative 2.25. The same values that we got in part A, part B. And let's see how to work out part D, I mean, for the case of Newton's backward difference interpolating technique. So in this case, we are going to use the same table as this one. Okay, let me just construct it, but the same table. But now, these are now backward differences. We'll have here x, and then f of x. So we have this horizontal line and the vertical line. So we have the first value of x is 1.0, 1.2, 1.4. For f of x, we have 0.1, 0.5, 0.8, 0.8. So the backward difference, the first order backward difference of f, that is 0.5 minus 0.1, that is 0.4. Here 0.8 minus 0.5 is 0.3. The same table as in the case of forward difference. So when you subtract, you get negative 0.1. But now how you read the table is what matters. When it comes to backward, you now read along a line that is sloping upward. So we are going to say that, of course, we need our x naught just like here, and f naught. And also, you know, the polynomial. So you'll write here that let our x naught be this one. This is our x naught. And so this will be our f of x naught, or simply f naught. So we read them along this line, so that the value here is the first order backward of f naught, and this other value is the second order backward of f naught. So what about the interpolating polynomial for the Newton backward difference technique? So you can write this, that of course the polynomial here must also be of degree 2. So that is P2 of x. But remember, it is a function of s. So P2 is always of x naught plus sh. That would be a function of s. That is equal to f naught plus s backward of f naught plus s plus 1 over 2 factorial backward squared of f naught. And so this is the same as our f naught is 0.8 plus s backward of f naught is 0.3 plus this is the same as s plus 1 over 2. 2 factorial is just 2. Second order backward difference of f naught, that is negative 0.1. And so again, let us simplify this one so that we see what we get. So with this one, we are going to get negative 1 over 20 s squared. So negative 1 over 20 s squared. Then plus 1 over 4 s plus 0.8. So this is a function of s, so this p2 of s. Let's get the derivatives. P2 prime of s is equals to negative 1 over 10s plus 1 over 4. And our P2 double prime of s, that's the same as negative 1 over 10. So let's see how to get the f prime of x and f double prime of x. F prime of x is the same as 1 over h times P2 prime of s. And so that is 1 over 0.2 P2 prime of s is, we got negative 1 over 10s plus 1 over 4. F double prime of x should be equal to, remember we are using chain rule, so that should give us 1 over h squared times P2 double prime of s. So that is 1 over 0.04 times negative 1 over 10, which is the same as negative 2.25. So now let's find s and then replace it. Remember the transformation that s is equals to x minus x naught over h. What is our x? We need the value when x is 1.1. 1.1 is here. So that's our x. Already we know x naught and we know h. So our x is 1.1. 1.1. Our x naught is 1.4. 1.4. And our h is the spacing between the x values. It is uniform, and so that is 0.2. So therefore, s will now be equal to 1.1 minus 1.4 over 0.2. When you press this in your calculator, Let's see what you're going to get. 1.1 minus 1.4, that is negative 0.3. Then we are dividing by 0.2. That is negative 1.5, negative 1.5, which is negative 3/2. So that's our s. And remember, when you differentiate, ds dx is the same as 1/h. That's why we are introducing 1/h here. When you use general, here it is squared because of the second derivative. So let me just say that ds dx is the same as 1/h. So let me now replace these values. So we now need f prime of 1.1. And remember, these are approximate values. They're not equal to. These ones are approximate. So this is approximately equal to, substitute s here. So we'll have 1/0.2 times negative 1/10 times our s, which is negative 1.5, then plus 1/4. We are going to get 2. And f double prime of 1.1 is also approximately equal to the value we got here is a constant, negative 2.25. So this is how to use those interpolating polynomials to be able to find the derivative of the function f of x. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving numerical differentiation. Bye-bye.